So, good afternoon to all of you. Welcome back. Thank you for joining in time. It is my honor, and you've seen her yesterday already, testifying what the program did for her as a researcher. But it is my honor to introduce Professor Nele van der Sikkel from the University of Ghent, where she leads a multidisciplinary research group focused on computational modeling, experimental and clinical analysis of cardiac arrhythmias. Originally trained in theoretical physics, she transitioned to computational cardiology to apply mathematical and network-based approaches to real-world clinical challenges. Her research integrates topology, network theory, and computer simulations to unravel arrhythmia mechanisms and optimize ablation strategies. As the recipient of multiple prestigious research grants, including the ERC Research Starting Grant in 2020, she has built an internationally recognized research team, bridging computational science and clinical electrophysiology. And her work has been honored by multiple grants, as I already said, as well as the AstraZeneca Award for Innovation in Personalized Medicine. Nele, can you start sharing your expertise, please?
It's my pleasure. I can only see you, Hilde. Is there anybody?
That's enough. Don't need more. No.
Yes,
I think
it's not
the students are in the, I would say, in the audience. You cannot see them. But again, and I
behind
urge you,
IT Institute icon or what?
okay, for the students, don't hesitate to raise your hand and to ask your questions, please.
Yes,
It's an
but it just I
pleasure.
wonder because I can only see four. I see Noah. I
Yes,
don't
but
see
yeah, that's because
Como.
we are the panelists. Yes.
Okay, yes. Okay, so I have no idea how big the group is, how many people are listening to me. It's
At
about
this moment, we are 37, which is way
yeah.
too late to you, and I hope more people will join in 2 minutes.
Okay. Okay. Okay, so luckily I can see Professor Stevens. But I will be talking to you today about interdisciplinarity to tackle the world's leading cause of death. And I will also tell you a little bit my story, my background, how I came to do this research. And I will also give some technical details, but I'll try to keep it simple. So in a way to inspire you how to do research that can really make a difference. So I'll try also to talk a bit about more general stuff. So I've been thinking a lot about what does it mean to advance science, like the bigger picture. And currently, so I'm overwhelmed, but I'm asking all of my colleagues, we are all overwhelmed with too many scientific papers. I don't know if the audience is responsive, but I wanted to ask if anybody has an idea on how many scientific papers are published each year, but I don't know if they can respond. They can?
They are able to put their answer in the chat. So please, participants.
If I see the chats, so people, you can put in the chat your guess.
Or in the Q&A, sorry.
So it's the webinar chat, huh?
It's in the Q&A. It should be, but
I see your
yes.
chat, but I don't see anything here. Host and panelist.
No, it's in the Q&A that they need to answer.
Yeah.
Several millions. Thank you, Danielle. Please
Yeah.
put.
Yeah, it's 2 million each year. So it's a lot, and it's 30,000 scientific journals. So it's huge. So as scientists, you're supposed to read all of this, not the 2 million, but the ones in your field. And yeah, I think if I asked all of my colleagues, how do you keep up? Everybody usually keeps up by going to the conference. So they're just too many. However, we do need to publish because publishing papers is what they look at when you write a grant. If you get a position, promotus, it's important for your status as a scientist. But once this is your measure, and it's already improved a lot, but people have been researching this as well, and it can lead to fractionation, so that you salami slice your data set into the smallest publishing unit, or reusing your data in multiple publications, duplicating papers, publishing results that are preliminary or incomplete, underemphasizing limitations, making exaggerated claims, data fabrication, falsification, plagiarism. This really happens, or happened a lot already. But also I found the paper, I was looking into it for the preparation of this talk, that the increase of the number of papers is actually mainly due to the number of brewing researchers. So the more researchers you have, the more papers you have. And that's actually the biggest factor that contributes to the number of papers. So my question to you is then, how do you make an impact in this enormous mass of science? So how can you really make it something done and that it actually changes? Another thing that is very important, and that you maybe already heard of during this course, I don't know, is the replication crisis. I'm going to talk here about one particular one in the biotech sphere. So there is a US biotech company, Amgen, that tried to replicate 53 high-impact cancer research studies, and they were only able to replicate 11% of it. Bayer, it's a German pharmaceutical company. They looked at 64 high-impact studies, and they were only able to replicate 36%. And then a professor here, John Ioannidis, he at Stanford University looked at 45 of the most influential clinical study, and he was able to replicate less than half of it. So I think it's an extremely important question, that not only that you publish papers, but also that you make sure that it's reproducible. So my second question is, how can you be sure that your research is reproducible? And the other thing that I want to think about is what happens with your results after they get published. So if I talk to all my colleagues and so on, very often you have maybe written code. That's something very common now. A thesis manuscript, but you get your PhD, nobody uses your code, read your thesis code or read your thesis code because it's not well documented. Also, very often, once a project is finished, there's no follow-up because the person who did the project went to another university and somehow there's no follow-up. Your paper just gets forgotten in the mass of the papers that is produced. You move on to the next project. So for me, each time that I do research, I always try to make sure that it's sustainable, that it doesn't go to waste once it's done, and that it fits in a bigger scheme of stuff. So the other question that I then want to ask is then, how can we make big leaps in science? Because a lot of the research we do is incremental. We also like to stay in our comfort zone. And taking a leap requires time and effort, and also slows the publication rate, and you need these publications for your CV. So what I always usually like to do is I combine things which have never been combined before, and it can be a good way forward. So this is like the interdisciplinary research is about combining different fields together, learning from different fields, and it's a way to do new and exciting things no one has done before you. So it's about looking beyond the borders of your own field. So for me, if you want to create impact, I think you need three ingredients at least. Your research should be reproducible, otherwise there's no use in what you have done. It should also be sustainable, so it should live beyond the paper. It should live beyond one talk at a conference. And somehow, it should be novel. And the way we are looking at here is trying to do interdisciplinary work. So these three things, I think, are crucial if you want to create impact. So I will tell you a little bit more about my scientific journey so far. So I did a PhD in physics. So this is me a long time ago. I did a master's degree in physics. I got my degree in 2007. I did my PhD in theoretical physics. So this is a picture of me when I was writing equations in Brazil. I was there 5 times during my PhD. And what I basically did was these kind of huge computations. I still did them by hand. I think you can now make them all do automatically. And in the end, you see it's just part of an equation because it doesn't stop you. It goes to the next page. And in the end, something had to be zero. All of this had to be zero, which it was. That was then the paper, or one of the papers that I published. I found it actually extremely boring because it was very, very mathematical. And I failed also to see the bigger picture. And my idea of doing theoretical physics was like very romantic, but in practice, it was doing this kind of stuff. And yeah, it's fun for a while, but after that, I just really didn't want to do it anymore. So I wanted to change. And what I did was a postdoc. There was somebody at university who wanted to work with me, and he said, "Do you want to change fields?" Because I didn't want to continue in the same field. And instead of staying in the same field, going to another university, I switched fields completely. I had no clue about cardiac arrhythmia. I also never programmed before. I didn't know how to do it. But what interested me in this research is that it was applied. At least you knew what you were doing instead of just writing equations. And yeah, I wrote, no, that's not true. The professor that I met, he actually wrote it. I didn't have a clue at that time what it all meant. But because I did my PhD I did pretty well in my PhD. I really got an FWO postdoc position in a completely new field. So there I was in a field that I didn't know. I didn't know how to program. So I had to actually start again from zero. And you see here, I had to start to learn how to program. I'm very happy now that I have a very nice team who does it for me because, yeah, it was really difficult, but I managed to do enough things to understand. So here you see the type of simulations that I did, the coding. And so I wrote a couple of papers that were pretty well received. But still, it was just theoretical. And still, I was again wondering, okay, I'm doing computer simulations. How do I go back here? I'm doing computer simulations of the heart. I still don't know whether what I'm doing is correct or not. So I wanted to do something even more applied. So I decided I was studying some arrhythmia called torsade de pointe, and I knew that in Utrecht they were doing experiments on dogs. And I wanted to go there and see whether my simulations were a bit the same as the experiments. So I did a research day in Utrecht Medical Center, and I wanted to check if my modeling was realistic. And I investigated experiments in TDP in a dog model. And so what they did, they had these dogs and they cut their chest open when they were under anesthesia. And then they put a huge number of needles in these dogs. I found these experiments extremely cruel. I don't think they're even allowed these days. But on the other hand, they were going to be done anyway. So when I saw that they did these very invasive experiments, I thought the least you can do, because so many animals were sacrificed, is to analyze these data and to do it really, really well. So when I was there, I actually saw that the group there, they were actually not analyzing their data to the fullest. They were only analyzing the first few bits of the whole data set. So the whole data set was a huge number of bits, and they were only analyzing the very beginning. So I wasn't thinking about, because they had very old software. It was a group who was doing experiments. And then I thought, like, okay, I will analyze these data, and I'm pretty sure I will be able to find much more in these data than what they had so far. So the thing was, on these data, they were all, actually, they were all electrodes here. And it was actually very noisy, bad data set. It was very sparse. I even had to guess the locations of these needles and so on. They didn't make a clear picture or an MRI or something. So the data there was also, with all the known methods in the literature, there was actually nothing to do with it. It was too sparse, too noisy. And I had to find a new way. And actually, that was the start of everything for me. Because I came to something also by talking to people, and I don't remember exactly how it went anymore, but I started to integrate network theory to analyze the data. And network theory is something that was not used before to analyze data sets. I will tell you more about it later. So it's actually a whole different branch of science. So it's something completely new, and I was the first one to use network theory to do something. So I will tell you more about it later. But in my second postdoc, so when I was doing these experiments, analyzing the experiment, I also followed the course at ITRH, the one you're following now. And it was, Hilde was saying, you really have to follow this. Your mind will open so much more than what you have now. And also I was already thinking about a patent, applying for a patent. So I completely lacked all the knowledge of everything. And this was extremely helpful for me. So it gave me a lot of new insights on the clinics and on the medical side and on everything around it, which I could begin. So actually it worked. Applying the network theory to analyze the data, I was able to show some very nice properties in these data. And then I was thinking, yeah, but I can apply the same idea to clinical data. So I can actually take a patient, take his data, because my method was so general, I could apply it actually to anything that I want. So I just went, I was here at Ghent University, and I was just thinking, okay, I will have to start to contact people. So I just went around and I started to look up everybody who was doing something around cardiac arrhythmia. And I contacted a huge amount of people. And one of these people was here, Matthias Duitsgraven. He's a very known electrophysiologist. And I remember I was there, I had this very crappy presentation for him. He's a very well-known EP, and his PhD student was sitting there. And I remember he was looking at us. I already had a student with me then, and he was looking at this when I was going to work. So I had this crappy presentation with his idea for what I wanted to do. And he said, okay, you get some data, test it, but you cannot know what the answer is. And let's see whether it will work out or not. And then you come back. And if it works, we can talk again. And it worked. Actually, I was pretty confident that it worked because in my mind, it already worked. And we just were able to show the location of arrhythmia, or in the patients, we could say where the arrhythmia was located. I will tell you about these details later. So first follow my story. So this idea was the start of my professorship. Then there was a position. I became assistant professor. And I took this idea to really all the next levels. I wrote an ERC starting grant for 1.5 million euros. And I got it, which was during COVID. I didn't even have to do the interview. So this was really the start, because when you get an ERC grant, university really likes it. So I didn't even have to do tenure anymore. I just became associate professor in 2021. So that's a bit my story on, I'm still associate professor. In the meantime, wrote many other grants, and I have now a research group of about 10 people. So I will tell you a little bit more now about the details on the ideas and how I'm integrating like the sustainability, creating impact, that it's reproducible, and the interdisciplinarity. So first, I will talk now a bit more about the details about the idea. So some basics about cardiac arrhythmia. So first of all, cardiac arrhythmia is the biggest cause of death. It's responsible for about 15 to 20% of all deaths. You might be surprised because you hear more about cancer. I think it's because also cancer is a disease that takes a very long time. It's very, it can be very lengthy. And if you have a sudden cardiac death, you just die within a minute, and there's not much to do about it. But so this is ischemic heart disease. So this is actually when you get an infarct and you die from that infarct. You actually usually don't die from the infarct itself, but you die from the arrhythmia that follows the infarct. And number two here is a stroke. Many people, when they have arrhythmias, the blood doesn't flow very well in the body and stays in the heart, and it starts to like form little lumps, and it can go to your brain and you can get a stroke. So if you have, for example, atrial fibrillation, you have a six-fold increase to a chance of having a stroke. So 1 and 2 are very often related to cardiac arrhythmia. So how does the heart normally work? So you have a sinus node, this is located here, and there's an electrical wave that starts from that node, and that spreads more or less evenly, very linear, through the atrium. So this is the right atrium, right ventricle, and left ventricle. And you have to follow the arrows so you see how the excitation of this wave, how it spreads. And this electrical wave that goes through your heart, it makes sure that there is calcium released in your cells, and that calcium will bind bind to some filaments and make these filaments contract. And that's how you get the contraction of the heart. So the electrical wave precedes the contraction, and actually in that order, your heart will contract. It will stop here. First, the electrical wave will stop here at the AV node, because here it delays, here the signal goes slow. And then it will fast go through this called a Purkinje fiber, through a network where it will then excite the left and right ventricle in such a way so you get this nice twist of the heart, so the blood pumps in the most efficient way. So this is how you should think of a normal excitation of the heart. So the important parts are right atrium, left atrium, right ventricle, and left ventricle. So there are 4 parts that are part of the heart. So very often when you have an arrhythmia, like this is here, suppose the mitral valve. So the mitral valve is back. The mitral valve is what connects these two here. The left and the left atrium and the left ventricle. So there is an opening, and arrhythmias like to go like this. So not all of them, but very often an arrhythmia is maintained by a re-entry. So this is an electrical wave, and instead of going nicely from top to bottom, the wave actually kind of gets stuck, and you can think of it as a Mexican wave. So here on the right, you see a Mexican wave, and it's the same principle. So each cell needs to get excited, and when the cell excites, you can think of a person standing straight, but the cell also needs to go back to resting state. So you need to sit back. And here you see that this black part is people who are sitting. The yellow part is people standing up. And if you see it rotating, that's the people who are continuously standing up. So it's important to see it in this way, because if people are standing up for a very long time and the Mexican wave goes around, and the people are still standing up, the wave will stop. And that's what usually happens in a healthy heart. So there's not a lot of space to do this. But when your heart is a bit diseased, it means that this Mexican wave moves a little bit slower. And by the time the beginning is back at where the people were, they already have gone back to their seats. So that's very important. So the wave slows down, so there's a lot of space for the Mexican wave to make its full rotation. So how are they going to treat it? So what they're going to do, so if that occurs frequently, sometimes it stops spontaneously, but sometimes it doesn't. There's actually no reason, once you have this Mexican wave in your heart, that it would stop by itself, because as you can see, it just keeps rotating. So it can go on like this forever. So it's kind of, the wave actually got stuck around an obstacle. What are they going to do if they want to treat it? If the medication doesn't work, they're going to try to make the wave, that the head and the tail, that they bump against each other. But if that doesn't work, they're going to go inside your heart and they're going to ablate part of the tissue. So they're going to go via your groin. They're going to put a catheter in. So via your belly, actually, they go in all the way into your heart. So you see here that they come in. And then they have to puncture a hole if they want to be at this part. and then they will burn a part of the tissue. So it's kind of a very invasive procedure, because what you're going to do is you're going to destroy healthy tissue. So they have to navigate inside this heart. I've been there many, many times. Navigate inside this heart, and they have to know where they are. And then they say, this is a spot, we want to destroy that spot, ablate it, so we stop it. But you can already understand it, because what are they going to do? They're going to, you can see it as a little wall that they're going to build next to your Mexican wave, so that the people don't see each other anymore. So if the people are standing straight, they can't see these people. So these people are just going to keep sitting in their place. So this wave just bumps against the wall and it stops. That's what they're going to. Of course, you don't want to scar the entire heart, or there's no function. So you have to do it wisely and don't destroy the whole atria, left or right. Because if they would scar everything, you need a pacemaker, because the heart doesn't function. So let me now tell you what are the types of arrhythmia. So there, basically, you can divide the arrhythmia in regular and irregular ones and where they are located. So the atria is the top part, the ventricle is the lower part. And if you have a regular arrhythmia in the atria, we call it tachycardie, and we just give it a name, atrial tachycardia. If it's irregular, we call it fibrillation, and we call it atrial fibrillation. So for the ventricles, we call it ventricular tachycardia when it's regular, and for the irregular, we call it ventricular fibrillation. You will not die from atrial fibrillation, you will not die from atrial tachycardia, you will always die from ventricular fibrillation, and you might die from ventricular tachycardia. Then there's one that is a little bit here, torsade de pointe. I did a lot of research on this. It's a little bit between tachycardia and fibrillation, because it's a little bit regular, but it's already also irregular, and it's also deadly, so I put it here. And I will tell you more about what I found in the most simple one, because my idea is always to start with the most simple one when I wanted to investigate what I found in this network theory, because it's regular atria. So it has to, if you want to test something, take your most simple. So atrial tachycardia, what they do, so they go in the heart and they make a map of your heart. And you can see it as taking a panoramic picture. So they're going to put catheters here, and they're going to measure the time when your electrical wave passes at a certain location. And because they have a reference catheter, so they know each beat, they know the cycle length, they are actually taking a picture, and they know at which time, compared to the reference, the wave is here, and so on. And because you take a panoramic picture and it's regular, you can do it. You just need to take the picture at the right time, and you can put everything together. And for a long time, they had to interpret just these color maps. And they know it goes from red, here you see, to green, to blue, to purple. And so if they wanted to know how the wave was going, they had to follow the colors, and they had to interpret the map and then say, okay, I see something is going around. This is the mitral valve again. Something is going around the mitral valve. But it had to be interpreted manually, and it's challenging and operator dependent. So you can give the same map to different doctors, and you can get even a different. Like here now, they improved the lattice mapping systems. They make now moving videos. So here you can nicely see this is in the right atrium. This is the tricuspid valve, and you see that something is rotating around the tricuspid valve. So here you see, this would be called, usually they would call it a typical flutter, but I will show you later that it's actually not a typical flutter. So this is what they have now. So they do the measurements, and then they get this map, and based on this map, they will decide, we will do an ablation line and build our little wall to stop our Mexican wave. So network theory as a new way to analyze cardiac arrhythmia. So I'll tell you a bit more about network theory. Google has a search algorithm, and it's actually based on network theory. What they do, all the websites, they link them together. So if you put a link on one website to another, it's the same as putting an arrow between two websites. And based on all these arrows, their search algorithm called PageRank is based on doing manipulations on this network. The brain is also a network. If you have a signal in one part of your brain, it will then go to another part of your brain, and so on. So you can also make networks in the brain. A lot of research on this. A food web feeds who. It's a network that always goes usually in one direction. And Facebook, here the arrows have double, because if you're friends with me, I'm also friends with you. So you have a difference between an undirected and a directed network. So this is undirected, this is directed. But when I had my idea, it was actually not, I almost found nothing on it that it was applied to the heart, although it's a very natural idea to transform cardiac waves into directed network. So I will show you here. So remember this rotation. So now it doesn't look like the Mexican wave because we didn't cut a hole out, but if you reduce the hole to nothing, this becomes your Mexican wave. It becomes more like a spiral. And so when you put your electrodes on the spiral, you want to know, actually what you want to know is you want to know where your Mexican waves, where they are located. And you see, if you put an electrode here, we did this virtually, so we just do experiments on the computer, you see again that where you have these spikes, this is the time when this wave front passes at this electrode. So here you have it. So what you get is when you put a grid here, you get actually all the times, we call it local activation time. We know all the times when the wave was at which time, at which position. And what we do is we connect neighboring electrodes. So this here, all the neighbors are this box here around. And if the time, we can divide the difference in arrival time when the wave was here, and we can divide it, we can divide the distance between the time, and we get actually a velocity. So we know what is the conduction velocity, what is the speed of the wave. We can compute the speed of the wave. So if the speed of the wave is acceptable, we draw an arrow. If the speed of the wave is not acceptable, we do not draw an arrow. And in this way, you can draw arrows with something that says how the wave is going. But you see, it's not always exact, but it doesn't matter because if you look here, the rotating electrical waves, so this network, you can now analyze it with methods that existed for 30, 40 years. You can find the cycles in the networks. These are the closed loops. And you see that there's a cycle here, but there are also cycles here. And if you take the middle of all your cycles, you get exactly in the center of your rotating electrical wave. So here you see it. This is a clinical case. This was one of the first cases we analyzed. We first also did the same. We were looking for the neighbors. We then leave the arrows that give conduction velocity that we like. We create a complete network, and then we find the cycles. And these cycles, they're exactly the cycles the doctor is looking for his ablation. So we wrote software for this, and we can actually just load the case now. A lot of years went over this to create something like this. And you just load the case, and you can rotate it and so on with the measurements. And we can now press just one button and see where these cycles are. But I will tell you a little bit more because something is still missing, something that we found. So you can see here, or a little faster. So here you see the loops that are being created. And yeah, these numbers you cannot understand. So we are writing a big software package and to do analysis of this data. And currently we are able to work with any mapping system, including our including simulated data. We do pre-processing, we do processing of the data, and we can find, you can ignore this for now, we can find the re-entries here. The rotors, they are the ones who don't have the, where the middle is gone. So this and this is the one I've been talking about. These are our Mexican waves, and we can find them on a huge number of different types of data sets. So now it's a very big software package. It has a lot of building blocks, and you can create your own pipeline if you have a data set that you want to analyze. It has its own pipeline. And so here already you can see something, because our new version is almost ready to go open source, source available with restrictions for commercial use. So we're going to have some hybrid methods that if a company wants to use it, they will still have to pay. But there's one thing that we were missing and that we were wondering about, and that was there was something bothering us. There was usually we found one cycle, but there was one reentry, but sometimes we find two, and sometimes we find one reentry. And we didn't understand what was happening. And also when we were playing with our parameters, sometimes there was a reentry at the place, and sometimes it disappeared again. And we thought, is it our data? Are we using the wrong parameters? What is happening with that second loop? Is it there or is it up there? So we started to look at the heart again from another angle. And we started, so in our field, everybody is making things more complicated. They're creating digital twins, they're adding more details to the simulations. And we said, let's go in the opposite direction. So what did we do? We just went to its most basic form. So here you have the heart, and we just said, okay, basically it's a sphere with 3 holes inside, because we have our pulmonary veins. These are the holes, it's non-conducting. We have our mitral valve. So basically it's just a sphere with 3 holes. And actually the right atrium is the same. We also have a sphere with 3 holes. We have superior vena cava, inferior vena cava, and this tricuspid valve. So basically 2 spheres with holes, and they are connected via one cable that conducts this electrical wave. And actually, many of the patients, they have scar tissue, but again, easy, because if there's scar tissue, it means that it's also non-conducting, and whether you have a hole or whether you have scar tissue, mathematically, it's the same. The wave will not pass through this tissue, so we can just see whether it's open or it's closed. For us, it doesn't really matter. So it's an additional hole in our system. And there was this paper, actually, this is a readable paper, but the same concept was published even in the 90s already. And it says that there are topological constraints. So topology is actually this here. So topology is deforming an object and saying that it has the same properties. So topology sees that this object and this object, they are the same, because you cannot, you don't create additional holes, but you can deform the tissue however you like. So this is topology. And it says that there is a constraint on spiral waves, so on these electrical waves in spherical geometries. And what they actually say is that, or what we also found and added to it, is that each of these holes, we can actually assign a number to it. We can give it a +1, a -1, or a 0 by computing some property. But we know that if we do that, in our sphere, the sum of the index has to be 0. So we did simulations on these spheres with 3 holes, and then we tried to compute this index. And the index, what does it mean? Actually, it means whether there is a complete rotation or not, whether there's a rotation or not. So this is very easy. This has an index of +1 because it goes against the clock. This one was easy. But this one not. This one was something that everybody has overlooked. So when the doctors saw this, they thought it's not important. But when you compute the index, and I will not go into details, this one gives a +1. This will actually give you a very nice -1. So not -1.1, -0.9. No, exactly a -1, +1 and a -1. And this here, you see parallel activation. So you see that the wave just collides with the hole. It just then goes around it, just it's like a stone in the water. So it doesn't really, it's not really bothered by this. But this is completely different from what you see here, because there's clearly something going around it. And you can actually easily compute. And so what we know from this theorem is that on each sphere, there has to be a -1, a +1. And what we found is that when you do an ablation line, you need to connect the -1 with the +1, and then you will always stop the AT. If you don't do it, you will not stop it, but you will get a slower AT because you make this hole a bit bigger. So it takes a bit longer for this wave to go around this bigger hole. And you will get a slower, and this one now also will become a full rotation. We'll have nicely 2 full rotations. And the crazy thing was, when we looked in the literature, this happened all the time. It happened all the time that when they did an ablation, that the AT became slower. But somehow nobody paid attention to it and was even questioning why it would happen. I think there was maybe 1 or 2 papers that were thinking about it, and they were a little bit in the wrong direction. But we just found a very simple reason why, when you do an ablation line, it sometimes stops and it sometimes doesn't stop. And we will also call this the critical boundaries, because something rotates around something. In AT, there's always an obstacle where it's rotating around, but even that doesn't matter. There are always 2 rotations. And if you now go to the sphere and you now go back to your original heart, it stays the same, because topology says if it's correct on the sphere, it will also be correct on the heart. This is really in the most simple, basic models with the most simple things you can even imagine. So this is actually very easy to do this type of research, because you need just very simple, very fast models. And also the thing is, nobody's doing this. So we were also the only ones looking at it, because nobody's looking anymore in the direction of simplifying. Everybody's making everything more difficult. So in that sense, we are, and still to this day, very unique, because nobody wants to do this type of thing. And so what is the outcome of this? I see I'm almost finished, but I think my presentation is almost done. So we got this published in European Heart Journal. This has like impact factor 40, so it's like nature for us. So I was really happy with this. Then it was published, all the details, where we showed proof of 131 clinical cases and over 500 simulation in a good journal for electrophysiology. Now we submitted the paper, but it will be accepted. We're working on the revision, but it looks good. Oh, no, not this one. This is the one. This is also revision. I think it also will be accepted. And this one, I'm more sure of this one. We are also trying to automatically identify where the critical boundaries are and improving our software. So we want to make everything fully automatic. So this is more clinical cases. This is improvement of the software. And for this, I also won the AstraZeneca award, as Hilde already mentioned, for personalized medicine and cardiovascular diseases. So I won it a few months ago. And actually, the biggest award is that Match has already changed his clinical practice, and he's getting a lot of attention because he's also talking about it in the field, that people are seeing it, and it's now starting to spread, and we're getting more attention. And in the upcoming guidelines for AT ablation, one of our figures will be part of the paper. So this is the paper that everybody who does ablations reads. It usually gets cited very, very much, like over 10,000 times. So this is really a very basic paper. So this will also give us a lot of visibility. So with my last minute, I want to say that we are now applying this to ventricular tachycardia, which is deadly. And we are actually finding the same thing. But there's a huge, I will not go in details in these slides, but there's a lot of complexity, because the ventricles, they have a thickness and they're no longer a sphere, but so your scar tissue can go from one layer, go a little bit into the wall, and then go back, which changes, you have to add an extra dimension. So I'll not go too much into detail, but it means that there are a lot of more possibilities, and this is what we're investigating now. And again, we have this very unique view because nobody else looks at it in the way we do. But already from looking at it, there's a lot of clinical implications that people are just overlooking, and that we know that will also change the clinical practice. Yeah, so these were the simulations. And we also see that the same holds for AF, and we're doing simulations on this. So my last almost my last slide. So if you want to create impact, I want to repeat, you have to be reproducible. So how do we do it? We have our software package, and then everybody will be able to use it and see that it works. So we can redo our experiments and reanalyze the clinical data. And other people can do it as well and see that we find the same. Sustainable, also the software package is our core business. So we wrote it in such a way that it can live for a very long time. It's fully documented. There's been many, many hours into this package so that it can really stand on its own and that people can actually use it. And I think I already gave a lot of insight that it's really interdisciplinary what we do. So my last slide is what did I learn? So I want to give you some difficulties with interdisciplinary research. So you have to learn to speak with other fields, which is not easy. Medical doctors, they have another language. They use different words for the same words. It takes time. You have to be willing to invest. You have to share data. There's a lot of privacy issues, material transfer agreements, all this legal stuff. Again, in the beginning, I spoke a lot to network specialists. That was another language. So I also had to invest a lot of time in learning that. You have to adapt constantly your style to the journal, to the brand panel of your choice. You have to learn not to write too technical, to write in a clinical way, which is not easy. You have to be able to explain things simple so the people you work with actually understand what you do. So this topology took me 2 years to explain it. But now they believe me. Now they know that when I say something, it will be like they try harder, I would say. Also, you have to listen to the doctors, what they want. You have to develop your method for them, their patients, not for yourself. So it's very challenging, but it's also a lot of fun. And yeah, if it's fun, you keep doing it. Voilà. Thank you. This is the end of my presentation. So thank you very much.
Thank you so much, Nele. Thank you so much for explaining what you do and indeed how your basic research, which really started at the base and learning a new language, as you rightfully said, had a true impact. And now, indeed, being included in the guidelines, that's like the biggest thing you can achieve, I would say, because this will have a true impact on patient. And I think this is indeed going from, I would say, a basic research project to true innovation. Thank you so much for sharing your insights. Indeed, communication and keep it simple is sometimes the best way. Reproducibility for sure, transparency is key in research. And I like, of course, and that's why we saw you yesterday. Thank you for that. Talking about the need for interdisciplinarity. Thank you. If there are questions, I see one in the Q&A. Anna Padisak said, a very interesting presentation. Thank you. You mentioned that you also started looking into atrial fibrillation. There is a lot of debate about its mechanisms. Do you have any ideas about it? Do you think there is only one mechanism behind it or multiple?
Yeah, there is indeed a lot
Oh,
of
sorry, Anya, you're here. Sorry.
so there's indeed a lot of debate, so you know it well. I don't know about the mechanism. Like, I think it's a very heterogeneous population, and I think that that's probably, it looks very likely that not always the same mechanism will be in the same, that different mechanisms will hold for different patients, because AF, when you measure it, it's actually just one signal that comes from an ECG that gives fibrillation, but it's actually a mixture of so many things that you can even simulate different mechanisms and get an ECG that looks very similar. So in that sense, it looks to me that there are multiple mechanisms going on. And there's a lot of debate whether there are like 5 or 6 big theories. And there's a lot of debate which one is a dominant, or in which patient which mechanism is going on, and it's a very long discussion to answer this question. So if it's rotational, they are going to also be with 2. So this I know, but there can also be other mechanisms. Some people say that there's dissociation between the 2 layers, and then the reentry just goes between the layers. Some people say there's micro reentry. There's many different mechanisms. So I hope to find out more if I can actually analyze more data. Are there any other?
Thank you.
Yeah.
Thank you, Anna, for your question. And I'm sorry I didn't see that you were promoted as a panelist, so you could ask your question yourself. If you have more questions, Anna, or the other students, don't hesitate to reach out. Nele will definitely answer.